Okay, this is chapter 19, problem 60, in which we're told that an ammeter's internal resistance is 53 ohms, and it measures, or it reads, 5.25 milliamps when connected in a circuit containing a battery and two resistors in series whose values are 720 ohms and 480 ohms. What is the actual current when the ammeter is absent? Okay, so we've got two resistors in series. One is 480 ohms, one is 720 ohms. Right, it's connected to some EMF. And then recall that in order to measure the current going through a circuit, you have to measure the current by actually sticking the device in. You have to break the circuit and stick the device in there to measure it. So you can think of it like this. This will be the ammeter. I'll call it A. And because it's not a perfect device, it actually has its own little bit of resistance, which, just for fun, I'll draw that resistance there with a smaller resistance, little r, we can call it, equal to the number that is given, which is 53 ohms. And as it stands now, this circuit has a current, which is read by the ammeter to be 5.25 milliamps. In other words, 5.25 times 10 to the minus 3 amps. Okay, and the whole question is, all right, that's what the current is measured currently, given with this imperfect ammeter. What would the current be in the absence of that ammeter? So it may be useful to really just think about this in terms of right now. It's a circuit with three resistors in series with each other, with the current known, the resistances are known, and that way, what you can do is you can solve for the EMF of the battery if you like. Then you can draw a similar picture without the ammeter in it and ask, ideally, what would the current be through that circuit. So let's go ahead and do that. So as it stands now, if you think about it, the total resistance, let's say real, is the sum of these two. So 720 and 480, if my math is correct, that's 1200. Ohms, but then you have this 53 ohm resistor in there as well, so I should write this as 1253 ohms. Okay, that is the total resistance in the circuit. You've got this battery in there as well. This whole thing should obey Ohm's law. In other words, the EMF is the voltage drop across the whole thing. That is the current times the total real resistance. So all you have to do is multiply these numbers together, and that would give you the EMF of the battery, 10 to the minus 3 amps times 1253 ohms, and that's 6.578 volts is what I find. Okay, that alone isn't so interesting. What you can now do is plug this back in and imagine that you've got a circuit now with these resistors being the same, 480, 720, the same EMF, but no ammeter in there, and now we can ask, what would the current be? Well, here the total resistance would be ideal, and it would just be the sum of these two, the 720 and the 480. That would be 1200 ohms. And then you could use Ohm's law once again. In other words, squiggly E, the EMF, is equal to the, if you like, this was the real current, and this would be the ideal current, times the total resistance. And so I can now solve for the ideal current. The ideal current is the EMF over the total ideal, which, by the way, I'm going to go ahead and point out that since we've already solved for the EMF, remember the EMF was actually the real current times the real resistance. So if you like, you can think of this as the ideal current is proportional to what the real current is, but then corrected by the ratio of the total real resistance divided by the total ideal resistance. If you want to think of it that way, you can. But anyway, we can use our result from before, that the EMF 6.578 volts divided by 1200 ohms, and we're expecting a number to be close to the real current, right? Because the total resistance is not much different from this, but it should be a number that's a little bit bigger. What you find is that this answer comes out to be 5.48 times 10 to the minus 3 amps, or 5.48 milliamps, which is a little bit bigger than the real current. This would be the ideal current in the absence of the ammeter.